Hi, my name is Jason Wong and I'm responsible for the GPS and temperature blocks.
My name is Kenneth Trung, and I was responsible for the transceivers and putting all of the Arduino code into one program.
My name is Kit Boyd. I'm responsible for the SD storage, the MATLAB, and video editing.
So our project was the Telemetry project. In essence, this project was about creating a device that could take outside environment inputs and send it to a MATLAB system half a mile away to display. Some of the inputs that the MATLAB system would display included a satellite map, as well as temperature readings and the voltage reading that was from the PCB that we created. For this project, there were some criteria we had to meet. I'll briefly go over some of the key criteria. Our first criteria was the system must operate for a long time. In this case, a long time was around 12 hours. Another requirement was the system must be accurate. This meant our GPS data and our analog voltages had to be within a certain tolerance of the actual values. Our enclosed system also needed to be robust, meaning it needed to survive some temperature requirements as well as being waterproof and also surviving drop tests. Our system also needed to send data half a mile away and display that data through MATLAB. One of the MATLAB requirements was to have a satellite map image. These two additional requirements were created by the team, and one of these was to measure temperature, and the other one was to store the data that we receive from our sensors locally on an SD card. Aside from these, there were also base requirements, which included that the system must not use a breadboard and that the system must use a student-made PCB.
This is the block diagram for the telemetry systems. All the blocks are color-coded for better visualizations. The telemetry itself consists of all the blocks that are inside this enclosure, and everything else, which are the three blocks right here, are the receiver that will be attached to a computer to display the result. The telemetry heart is a Arduino Uno, which controls two sensors, a GPS sensor and a temperature sensor, as well as a wireless transmitter and an SD storage. The system is powered by two 9-volt battery. One will be powering the Arduino, as long as the sensors and SD storage, and another one will go through a 5-volt regulator, and that will only power the wireless transmitter.
I'm going to be talking about the GPS and temperature block. Starting with the GPS block, I was tasked to find a GPS module that would satisfy our engineering requirements, as well as being affordable. The module I picked up was the Neo 6M. I picked this module because it was able to satisfy our engineering requirements for providing GPS data within a 10-meter accuracy of its current position, and its ability to receive and send data out at least once every 30 seconds. The cost of this module was $16, which is a good price for the functionality it provides. With the addition of the module being well documented, it made it easy to implement code to test the block. Here's the code I used to test the block. Using the tiny GPS library, I was able to easily parse the data received from the GPS module and display the longitude and latitude data in a neat and easy format to read. This is the temperature block. For this module, I picked the TMP36 temperature sensor. This module satisfies our engineering requirement for operating at a temperature range of -10 degrees to 85 degrees Celsius. In addition, it also needed to record temperature data within 1 degree Celsius from the surrounding area. This module is also well documented, so finding formulas for temperature calculations was made easy. The testing code that I've used simply takes the analog voltage from one analog pin on the Arduino and does some arithmetic to produce temperature values for Celsius and Fahrenheit. Both the testing codes will be stripped and merged with the transmitter code later on.
I am going to describe the SD card module. These are the physical layout of the SD card module. This is a generic, widely used SD card module, and I bought this version from the Techbot store. It is very cost effective, as it only costs $2 to $3. It's used an SPI interface, and it supports the FAT16 or 32 data format. The code for this Arduino is provided in the public library of the IDE, and it is a simple use of the library sd.h and sp.h. The functions that were implemented include sd.open, sd.close, and zero write.
This is the transceiver module we decided to use for our project. This is called the HC12 and it is a wireless serial port module. This module operates at 433.4 to 473 MHz. It has 4 operating modes known as FU1, FU2, FU3, and FU4. At FU4, this module has an operating range of 1,800 meters in open space. This is the code that I wrote for our transmitter block. To keep it simple, all of the work is really done within this loop. This loop only runs when the GPS module is connected to the satellites. When it is connected, it collects data such as the hour, the minute, second, latitude, longitude, as well as the temperature and the PCB voltage. After it gathers all of this data, it converts them into strings and sends them to the receiver. It also sends a special character at the end to help the receiver identify where the end of each string is. Afterwards, we open up a text file to write all of our data inside of it. At the very end, we delay the program by 15 seconds, so we have 15 seconds in between transmissions to help reduce our power consumption. This is the code that I wrote for the receiver block. This code does is it waits until the receiver has received something from the transmitter. When it does, it reads the stream until it hits the special character as mentioned before from the transmitter. Afterwards, it prints out that data onto the serial monitor and it repeats for all of the different types of data that we sent in from the transmitter, including latitude, longitude, temperature, etc.
The last block to this system is the MATLAB display. The MATLAB script is built from an open source script provided from GitHub, originally developed by Zohar Bar Yehuda. In this script, MATLAB directly reads input from the serial monitor via a serial connections with the receiving Arduino. MATLAB displays the temperature, the current positions as a red dot, and 5 older positions as the black dots in the final result. The figure is made using dummy variables. I am going to talk about the PCB for this project. This is the silkscreen layout for the PCB. It has is only two-sided. This is a simple small PCB for the L7805 5V voltage regulator. All the components on this PCB are surface mounted, and it serves as a power supply for a transmitter. So a 9V batteries will be connected on this side, and it will output 5V on these 5 pins. This version 1.0 actually needs a lot of improvement as listed in the patch notes. The reason why this PCB is needed is because the Arduino can only output up to 50 mA of current, while the transmitter can draw at most 100 mA while transmitting.
Some difficulties that we encountered while working on our project was learning to use KiCad to build our PCB. It was a software none of us had used before, so we had a difficult time learning how to build a board. There were many aspects of building a PCB we never considered until we have had our board reviewed by our instructor. We've also made the mistake of not testing the range of the transceivers when we first bought them. The transceivers were rated for a range of over 1,000 meters, but their testing conditions and equipment used to achieve this range was unclear in the datasheet. For our future improvements, there are several parts of our project our team would like to change. First, we would like to design and 3D print our own enclosure instead of purchasing one to save money and to personalize our system design. The second improvement would be to thoroughly research and invest on new transceiver modules that would meet our engineering requirements for reaching a range of half a mile. Lastly, we would like to improve our PCB design by revisiting our schematic, trace widths, labels, and space management on the board.